Hello, everyone. This is Dr. Daniel Mayo, and this is the very first of the video lectures for the course Introduction to Machine Learning. I'm going to be starting off with a PowerPoint presentation to be able to introduce some of the images and some of the categories a little easier, and then I'll move to board work where we'll have a blackboard, and I can write in all sorts of nice colorful pens, and hopefully it will be a nice analog to the home ground class. So here we go. First off, what is machine learning? Well, machine learning is kind of a intersection between mathematics and computer science, where the math is calculus and statistics, and the computer science is really clever algorithms, which I think you'll enjoy quite a bit as we get into them. Um, the main reason why machine learning has evolved is it allows the computer to learn to do a task without being explicitly programmed. So we have tasks that would require thousands and thousands of lines of code if you actually had to code it in manually. But with a simple algorithm, it can do everything and learn what it needs to learn with just a few hundred training examples. But let's go through some of the examples of what machine learning is doing right now, what it's being used for. And we start off, there's the self-driving cars that's using machine learning. You can't imagine how difficult it would be to have code handling all of the millions of variables that would pop up throughout normal driving. And instead, we just have algorithms that learn uh, when it should brake, when it should turn, and all of that. And so far, it's working rather well. I suspect we'll have autonomous self-driving cars legal on the roads within probably 3 years or so. Another example, which I'm sure most of y'all are familiar with, is auto tagging. So in Facebook, when you upload a photo, it suggests who the faces belong to. That is definitely machine learning. Facial recognition is all about machine learning. It handles facial recognition and any kind of image recognition extremely well compared to normal algorithms. Also, if you have used Netflix or Hulu or Spotify or shopped at Amazon, you have had things recommended to you. I am amazed at how well the algorithms are able to track what you like and don't like. Um, right now, my list of Netflix movies that it recommends are very accurate to the ones that I would actually enjoy. A lot of science fiction, post-apocalyptic zombies, things like that in my list. But being able to learn what a user enjoys, what their tastes are in movies and music and their buying items, all of that is machine learning. And it learns your preferences and makes really good suggestions most of the time. And finally, when I think of machine learning, I think of teaching a computer to be able to beat a human at a game. And this right here is an image of when AlphaGo beat the world Grandmaster Go champion. People thought that this was impossible. This happened back, I believe, about 3 years ago. Um, and at the time, everyone said that the game of Go was much too complicated for a computer to be able to handle and beat someone who was at the Grandmaster level. Turns out they were wrong. Machine learning was able to not only adapt from learning what the humans had programmed into it, but because it is learning itself, it was able to develop strategies that no one had ever seen before in the world of Go. And if you haven't played Go, Go is played on a grid with black and white stones, and the complexity of it is analogous from what I've heard. Go is to chess what chess is to checkers. It's extremely complicated and challenging, and yet machine learning algorithm, a very complex machine learning algorithm with a very fast computer, was able to beat the world grandmaster champion 4 out of 5 games when they played, which absolutely took the world by surprise. So hopefully you're inspired not only by all of the things that I've got up here that you can use machine learning to do, but it is the using machine learning is the #1 job in America 3 years in a row, data scientist. It's one of the highest paying jobs. It is one of the most challenging jobs because you have about a 60% turnover rate in your knowledge base every single year. 60% of what you learn and use one year has been, I won't say rendered obsolete, but it has been superseded and advanced upon by the next year. So you have to constantly evolve as you do your machine learning. It's something that is always changing. But one of the best features about machine learning, not only does it pay well and is it very challenging, but since machine learning is touching every single job market that you can think of, everywhere from the textile industry to video games to sales, in every single part of the job marketplace is being touched by machine learning. So if you have a particular niche that you want to work in, odds are you can apply machine learning. So it makes it a very desirable skill to have on your resume, because almost any company in any of the job sectors can use machine learning. So now that you're fully inspired, let's move on and talk about what is machine learning. Oh, well, before we get to that, let me actually explain why it blew up. Why is machine learning happening now? Why didn't it happen earlier? It's kind of strange to think about, but most of the algorithms, at least the basis of the algorithms that are used today, were developed decades ago. Some of them in the 1960s, before computers were even a thing. Why did it suddenly explode 5 years ago and up till now? It did that because two things. Big data. In order to train your models to where you can have accurate models that can make good predictions or can do other things accurately, you need massive amounts of data. Some of the machine learning models don't train on hundreds or thousands. They train on millions of data points. And we just didn't have access to that kind of data until recently. And along with that data, you can't process that much data. And some of these algorithms are extremely computationally intensive. You can't do that without faster processors. Once we started seeing the processors get to multiple cores, a handful of years ago, probably more like 10 years ago, things started progressing to where they could run some of the algorithms, and as time has moved on, those algorithms have become more and more complex, and the processors have been developed that can keep up with that. So that is where we are now. We have the big data to train our models, and we have the processing speed in order to actually do all the calculations in a reasonable amount of time. So there are 3 main categories that you can break machine learning down into. The first one is supervised learning. So supervised learning is where your data is pre-labeled and it's already sorted. It has a right answer given to it. These are the ways that we typically think of data. Things like you have done a survey and you've gotten actual, numeric answers. Uh, you have done a survey. You've actually looked at housing prices in your area. You have square footage for your houses, and you have the price that they sell at. Uh, you have data that is actually um, labeled in a way that you can use it. Your algorithms can then say square footage, price, and that way you can just feed the examples in one by one, and it can use that to train its model. Um, there are typically two main categories that you use data that has been labeled. One of them, which we've kind of already talked about, is to make a prediction using regression. And in regression, you have a set of training examples that are discrete training examples. So, in other words, you have dots on the graph. All the little blue dots represent actual data points of square footage versus house prices. And what we want to do is be able to use that data and find a continuous value prediction. We want to have something that I can feed any square footage value into, and it will predict a price as the output. Um, Regression is all about training examples leading to being able to make a prediction of some sort. The second main use for labeled data is classification. Uh, this is an extremely important area of machine learning because this is where you're able to sort items into categories. When your email notifies you that you have spam, it has identified that an incoming email had characteristics that match that of what spam has. And so it's able to sort it into a spam folder for you. That seems trivial, but the exact same algorithms can be used to tell whether or not a tumor is malignant or benign, whether someone has skin cancer or doesn't. Um, all of this is being able to take data, lots of data, train a model, and then you give it an example of the same type of data, and it's able to say it belongs in one of the categories. And this is also how it handles if you're trying to tell the computer whether or not an image is of a cat or a person. The way you do that is you train it on hundreds of images of people and hundreds of images of cats, and every single image is labeled as human or cat. And once you have your model trained, you feed it an image of a cat, and hopefully it will classify it as a cat if you've trained your model right. So those are the two main subcategories of supervised learning where our data is labeled. It'll make more sense next with the next category because that one is when you have unsupervised learning. And in unsupervised learning, we have uh, data that is not labeled, generally massive amounts of data that is not labeled. Um, the main reason that you want to use unsupervised learning is to try to pull structure from what appears to be random data. This is very important in many cases, but I would say 80% of machine learning that is done on supervised, maybe 5% is unsupervised, and the other 15% is on the last category, which we'll get to. But so unsupervised learning doesn't have, it's not used anywhere near as commonly as supervised, but it is extremely important in some cases. For example, on the screen, you have t-shirts. You have the height and weight of a customer, and then you have these discrete values where the height matches the weight, and where you have height and weight, I should say. And then what you want it to do is to break that data into categories. And in the case of t-shirts, you probably are going to have categories of small, medium, and large. So you'll feed it just a scatter plot of the data, and it will work at breaking the data into categories that make sense. And if it does it right, you can actually say that the upper right category is the large size t-shirts. That's what they should order, and the medium for the medium and small for the small. That seems like a very trivial example, but you can definitely see how that would help you with market segmentation. You take characteristics of your customers, and then you are able to pull out groupings that you can then use for advertising purposes or whatever. So it's very important in some aspects of business to be able to do that. That's the clustering, where you break things into groups like that. But I actually think non-clustering is more interesting. This is very rarely used, but it is used. Specifically, astronomy likes to use this one. It's where you have completely seemingly random chaotic data, lots of data. What you do is run machine learning algorithms on that data, and all it's doing is it's looking for some things that might be different, that might look odd. Humans may not even be able to detect it looking at the data, but the machine learning algorithm can notice patterns that we can't see. In astronomy's case, you have giant data sets of star information from telescopes. What it can do is actually pull out anomalies from that star data. That's why, if you've been following astronomy news over the past 3 years or so, the number of exoplanet discoveries, examples of gravitational lensing, binary stars, quasars, any of the astronomical anomalies, they're being discovered at an exponentially higher rate than they were just a few years ago, because they're now feeding the star data into algorithms, and the algorithms are really good at spotting anomalies, whereas a human won't even notice it. And honestly, in the case of astronomy data, it's too big anyways. A human cannot stare at a screen and process, a petabyte of data, which is what the large telescopes generate every single day. So you have to have algorithms at some point, and it turns out those algorithms are really good at what they do. So unsupervised learning is data that really doesn't have labels, and you're trying to pull out some sort of signal from the noise. In the case of clustering, you're trying to group. In the case of non-clustering, you're just trying to pull anomalies out of the data. Alrighty, and that leads to the very last main category of machine learning, and this is the one that most people think of when they think of artificial intelligence, because this is reinforcement learning. In reinforcement learning, your algorithm is learning how to perform a task based on a punishment and reward system. One of the best examples of this is being able to train your machine learning algorithm to be able to play a video game. It doesn't know anything about the video game. All it's going to be doing is looking at its score to tell how well it's doing. And it learns pretty quickly that if it runs into a pit and dies, that's a punishment. So it tries to maybe run really fast at the pit. Well, that doesn't work either. It falls and dies again. Then it tries to jump into the pit. Well, that doesn't work. Then it tries to jump over the pit. And then it gets to continue. And once it sees that it's able to continue and get a higher score, it learns that when it sees a pit, it jumps over it. That is the proper response. And so it will gradually learn how to perform a task based on punishments and rewards. And this is actually one of my favorite aspects of machine learning. Watching a program learn how to play a video game is creepy and awe-inspiring at the exact same time. Um, they now have it to where within, 37 lives, an algorithm can learn how to beat Super Mario, the very first world of Super Mario. Uh, that's incredible that it only has to die 37 times before it learns how to avoid the pits, avoid the monsters, learn when to jump, when not to jump, all of that. It's able to do it. So reinforcement learning is, I think, it's the most exciting part of machine learning. Alrighty, so we are now going to move into the first machine learning algorithm. It's going to be the easiest machine learning algorithm, and we're going to start with uh, linear regression. This is supervised learning, and I'm going to be switching to the Blackboard so that I can actually write it all out, and I will see you there. Okay, so here we are. We are now at the Blackboard, and uh, we are going to be going over linear regression. Before we can jump into linear regression, though, we need to establish some definitions. We'll be using the definitions for the rest of the course, so it's definitely worth a little bit of time to actually learn them. The first thing is that, as I've been saying throughout the first part of the video, is that we in machine learning use, I'll get this writing thing down, training examples. We don't typically call them data points. We call them training examples because they are what we use to train our models, each of the data values. So if I have multiple training examples, well, that leads to the training set. So the set of all the training examples is the training set. And this is where we are going to diverge from typical mathematics, and the number of training examples is going to be given by, here we go, different from all math you've ever had, M, not N. In machine learning, M is always used to designate the number of training examples that you're using. Okay, so we're going to call the X are going to be our input, and then our Y are going to be our outputs. And if I want to think of a training example that is labeled, well, the training example will have an input and an output that we can use to train with. In the case of the housing prices, we're going to have X as our input, would be the square footage, and then Y is going to be our output, and that's going to be our price. So we've got our input and output as a kind of a coordinate pair here. And in order to be able to reference individual inputs and outputs, we're going to be using the notation that will come back, and we'll see it over and over and over, and you will eventually get used to it, I promise. But if I am talking about the ith training example, I use xi as the input. So this is the ith input, and then y, I, if I can do the little dot, that is going to be the ith output. So note that when I am accessing, let me draw that y a little bit better there. When I'm talking about my xi and my yi, I'm going to try to be very careful and say it like that, instead of as x sub I or y sub I. However, after having been calling every single time I'm talking about the I object as x sub I and y sub I for a long time, many, many years, I will slip and I will say x sub I, y sub I, but in machine learning, what I really mean to say is x superscript I and y superscript I. But I will slip. It is a guarantee. I will do my best, but it's going to happen. Just try to ignore it and know that I mean x superscript I and y superscript I instead of the sub that I will wind up saying. So if we have that and I'm talking about the ith training example, well, that's going to be the coordinate pair now where we have xi, yi, and that is going to be the ith training example. So this is the notation that we're going to be able to use from now on. Alrighty, so with that, here we go. And you'll hear me probably in the microphone turning my notes around. You may even hear a cat meow or two, so who knows. Alright, here we go. Let's see if I can clear the screen. There we go. Perfect. So we are now going to talk about a function that maps inputs to outputs and outputs. So in our case, we're talking about I need a function that is going to map our inputs to our outputs, our x's to our y's, and I am going to call that function h. Okay? And the way that this is going to flow is I will have a training example. Oops, the G there. And then I will then feed that into some sort of learning algorithm. And then that will be used to develop my function h that will then accept as an input my x's, and it will output my outputs or my y's. So this is the model that we're going to be using. We're going to have training examples to train the algorithm, and as it is trained, it will result in a function that we can then take inputs into, and then we'll get a good prediction with our outputs. Alrighty? So that is going to be the basis of what we're doing with our linear regression. And so now that I've been saying the word linear regression quite a bit, let me actually define it a little. Here we go. So when I say linear regression, I'm talking about I have a set of data points, and what I want to do, just like with the housing prices, if I have an input, maybe it's square footage, I want to output price. And the way I'm going to do that is I'm going to train my model, and it will result in hopefully a straight line, which I can't draw, but I try my best, to where now if I input any value of square footage, maybe right here, and then I come up dash, 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 up to here, and then I look at the output for that line is going to be my y value, and whatever y value, oh, I just lost my pen. Why is my pen not working? There we go. There we go. Right there will be the price that is my predicted value. Ooh, that was weird. Well, my pen is doing strange things. Hold on. Okay, I just cleared that because my pen was misbehaving. So what we're trying to do is get the prediction right here by using our model. Okay, so with that in mind, what we want to do is find the line that best fits the data. That's what we're going to use as our function. So another way to say that is our line that we are looking for. That is going to be our h function. Okay, so here we go. Let's start off with an equation that describes a line. So maybe we have y equals mx plus b, where b is our y-intercept. It's where the function crosses the y-axis. Another word for that would be your baseline or your offset. And then our m is going to be the slope of the line. So since I have my y is given from my x value times the slope plus my y-intercept, what I can say is that this function right here, this y, is really what my h is supposed to do. So I'm going to rewrite this as h is equal to theta 0 plus theta 1 x, where I have my y-intercept is down here at theta 0, and my slope is going to be over here as theta 1. Okay, I just reordered it. There's a very good reason for reordering it in this way, and I can even go so far as to say now the h is a function of an x, and that is given by theta 0 plus theta 1 x. All right, so all I'm going to be doing is trying to develop a model that will yield an h function that will allow me to input an x and get an accurate y out. Now, every single algorithm has to have a way to evaluate how well it does. So the way that we are going to evaluate how well our algorithm is performing is through what is called a cost function. A cost function is used in almost every single machine learning algorithm. Its sole purpose is to evaluate how well a model is performing. Okay, so we're looking to develop a cost function that will tell us if our model is doing a good job or a bad job at predicting house prices. Okay, we are going to give the cost function a special letter. We are going to give it the letter J. You will be using the letter J to represent cost functions from here out. And in our case, if we're talking about a function that looks like this, we're going to be evaluating how well that's performing by looking at theta 0 and theta 1 with our model. If I input a y-intercept and a slope, how well does my model perform with that y-intercept and that slope? How well does it actually predict the price of a house based on its square footage? So I'm going to call this my cost function. It's a function of my theta 0 and theta 1. And I'm also going to make a definition and say that my h of x right here is going to be called my hypothesis function. So we have a cost function which evaluates how well the model is performing. The actual function that's used to make predictions is going to be the hypothesis function. Okay? Those are two concepts that will be used in almost every single machine learning algorithm. Alrighty, here we go. We are nearing the end of the lecture, so stay with me. So what I want to do now is talk about how the cost function is going to work. When I have linear regression, let's say I have a really simple model. I have just a few data points, and I'm going to fit a line to these data points. So I'm going to make a guess with my model. And let's say I make a guess and it is something like, oh, I don't know, let's do a really bad guess. That's the line that fits the data. Well, that's a really bad guess because it's way below every single one of my data points. Alrighty. So I know that one is not an ideal case, so I'm going to erase that. If I can get to erase. Come on. It'll erase. I'll get the hang of this, I promise. Oh, there it is. Okay. I was using the wrong function. Silly me. So here we go. We're erasing that line. Oh, that's cool. So here we go. Now, I do a line that looks like that. Well, again, that's an okay, good guess, but I guess it's not the best guess. It doesn't fit the data the best. So we'll take care of that. What I want is something that fits the data very well. And when you think about what the difference between this line and the previous two, what makes this one a better fit? And what makes it a better fit is that it is the closest to all of the data points. It's close to this one, and this one, much more so than the other two lines were. So a way to measure whether or not your guess, your regression line is performing well is to evaluate the distances between the actual data points and the lines. All of these distances. And so what I could say is the vertical distance, I'm going to call the y value for my line y hat. That means it's a predicted value. I'm going to call the actual y value of the data points just plain old y. And so the distance between my predicted line and my actual data point right here is just going to be y hat minus y. Okay? And if I want to use the machine learning, I can say it is y I hat minus y I. For a given training example, the ith training example, this is the distance between the prediction and the actual value. Okay, I could give this a name. I'm going to call it error, but you may have also seen it as residual. A residual is just the difference between the predicted value and the actual value. But we're probably going to just stick with error because that is a more common way in machine learning to refer to that difference. Okay? And so in order to be able to add up all of the error for each of the data points, I can't just sum. I can't do this. I can't just say the sum of all of my y i's, y hat i's minus y i's. I can't just sum it like that because some of the data points are going to be below the predicted values, some are going to be above the predicted values, and so I'll wind up with positive and negative values from this that will wind up canceling each other. And in order to make sure that the distance is always represented as positive, I could throw in an absolute value. That's one way. That is a not good way to do this, though. That is a terrible way for the mathematics that's coming. So instead of doing the absolute value, I'm going to erase that. I am instead going to take this and square it. If I square that distance, that difference, it will all be positive, and then I'll add it up. And this right here has a special name. This is the sum of the squared error. Okay? But if I want to be able to compare a data set that has 3 values versus one that may have 1,000 values, I can't just add all this together, because the one with the larger number of values would always have a higher sum of squared error. So in order to normalize it to where I can compare any set of data, I am going to divide by the number of training examples that I'm using. So 1 over m times the sum of the y hat I minus the yi squared. 1 over m, when I divide by that, it gives me the average, or as will be more commonly used, that is called the mean. And so what I have here finally is the mean squared error. And that is known as MSE. MSE is the default way of evaluating whether or not a model is doing well, or it is probably the most commonly used method in simple regression type predictions. It's just mean squared error. So that's where that's going. And since the mean squared error tells us how well our model is doing the prediction, we can think back. We've already said that that has a very special name, and that is, drum roll, that is our cost function, our J sub theta 0, theta 1. So our cost function for linear regression is going to be the mean squared error. And all we're going to do is develop an algorithm that will minimize the mean squared error. If I can minimize my error, so if I can take my MSE and then minimize it, I will have found the best fit for the data. And that is where we're going to head in the next lecture. So I hope you enjoyed this, and I will see you next lecture. Take care.